In this video, we are going to talk about quotients of vector spaces. This is our overview slide, which we'll spend about 5 minutes going over before we go over each topic in more detail and with more examples. We start by defining a vector V plus a subspace U. So suppose V is a vector in a vector space V, and U is a subspace of V. Then the vector V plus U is the subset of V defined by V plus U for all vectors U in the subspace U. This here is a picture of our first example of V plus U. So let's say our vector space is R2, so it's this entire plane. And let's say U is the subspace here. It's the line such that y is equal to 2x. So in other words, we have our x coordinate and then our y coordinate is 2x. So it's this line that goes through 0, 0 with slope of 2. This is U. Now, if we want to look at V plus U, and let's say our vector V is equal to 17, 20, that means each point on our line U gets shifted over by 17, 20. So when we're at 0, 0, we get shifted over to the right 17 units, and then up 20 units. So actually this should go up a little more. And then when we're at the point 1, 2, over here, we should be going up again, shifting over 17 units to the right and 20 units up. So we get the point 18, 22. So you can see what this V does to U is it shifts all of U over by a distance V, and it shifts every point over by the same amount to the left or right and the same amount up or down. Once we add a vector V to a subspace U, we have what we called an affine subset. So here's the definition. An affine subset of V is a subset of V of the form a vector plus a subspace. And then we use this definition of an affine subset to define what it is to be parallel to a subspace U. So an affine subset is V plus U, and that's said to be parallel. So U has to be, the entire subset has to be offset by V in order to be parallel. Now we're going to group all the affine subsets for a particular subspace, and we're going to call it a quotient space. So suppose U is a subspace of V, then the quotient space, which will denote V over U, is the set of all affine subsets of V parallel to U. In other words, the quotient space V over U is equal to V plus U for all the vectors V in the vector space V. We have this theorem here that two affine subsets parallel to U are either equal or disjoint. And then we can also define addition and scalar multiplication on the quotient space. So then we can say that the quotient space is itself a vector space. Next, we have the quotient map. So suppose U is a subspace of V, then the quotient map is the linear map from V to a quotient space. And the natural mapping, which when you really think about it, is the obvious mapping, and we're going to define it or notate it with the pi that goes from V to the quotient space V over U. That pi takes a vector V in our vector space V and it maps it to V plus U in our quotient space. We have this theorem, dimension of a quotient space. Suppose V is a finite dimensional vector space and U is a subspace of V. Then the dimension of the quotient space V over U is equal to dimension of V minus dimension of U. Finally, we have this induced map notated with a tilde over T. So suppose T is a linear map from V to W, then we can define the induced map, this T tilde, the quotient space of V over null of T to W by our induced map T tilde on V plus null of T is equal to TV. From there, we have this theorem that relates several different things, and we'll go over it a little bit in our video. That concludes our overview, so we're ready to come back and start looking at each of these topics in more detail. We start by defining the products of vector spaces. Suppose we have vector spaces v1, v2, up to vm. They're all vector spaces over a field F. Then the product v1 cross v2 cross up to cross vm is defined by vectors v1, which comes from vector space 1, vector v2, which comes from vector space 2, all the way up to the last of the m tuple vm, which comes from vector space m. Our example was if we had the space of polynomials of degree 2 or less crossed with the space of vectors R3, then our results are going to be elements of length 2 with the first item from the space of polynomials 2 or less, and the second item from R3. So an example is here this n tuple, our ordered pair, where our first element is from polynomial space of degree 2 or less, and our second element is 3, 8, 7, a vector in R3. We can define addition on this cross product as if we have the first m tuple at u1, u2 up to um, and our second m tuple, v1, v2 up to vm, we add component by component. So the vector u1 plus vector v1, vector u2 plus vector v2, up to vector vm plus um plus vector vm. So for example, looking again at our P2 cross R3, taking our polynomial 5 minus 6x plus 4x squared, as well as our triplet, our vector in R3, 3, 8, 7, we can add it to our second P2 cross B3 element, a polynomial 2x minus x squared, and then our R3 vector 1, 0, 1. When we add that, you notice we add our polynomials together and then our R3 vectors together. So in other words, we're adding the same type of vectors to each other. We're not sort of mixing them up and mixing them around. So our addition and scalar multiplication will make sense. And finally, once we have our addition and scalar multiplication defined, you might have guessed, then we're going to say that the product of vector spaces is a vector space. The next thing we will look at are quotients of vector spaces. And we will start by looking at this vector v plus a subset u. Suppose V is a vector in vector space V and U is a subspace of V. Then the vector V plus U is the subset of V defined by V plus U for all vectors U in the subspace U. So writing this down, our vector space V then is R2. U is our set of points such that this Y vector, the second vector, is equal to twice the first vector. In other words, y equals 2x. So it's the set of points along the line y equals 2x. And that's this, it goes through the point 0, 0, and as the line was sloped 2. So this is my subspace U. It's the line, and it's a subspace of R2. Now, if I want to add V to U plus V, to every point that I have on U, I'm going to add V. And if V is 1720, that means to 0, 0, I'll get 1720 plus 0, 0, which is 1720. If my point is 1, 2, then my V plus U is going to be 1822. So I can plot these points, right? My 0, 0 then becomes this point here, 1720. And my 1, 2 becomes this point over here, 1822. And you can see what's happening now. Each point on this line, U, is getting shifted over by V. So V shifts U over, and every point on U is shifted over by the same amount, the vector V. So in other words, every point is shifted over to the right 17 units and up 20 units. So what you see is U is just kind of shifted over by V. This next example has our space V in R3. So our vector space is R3, and our U, our subspace, is going to be the XY plane. In other words, where the Z value, or the third coordinate, is equal to 0. So U is equal to this plane here. Now we want to consider U plus V. Once we determine our vector v, every point on u then will be shifted over by v. So totally analogous to our last example, what v does is it's going to, in this case, because v is positive, it's going to raise our plane up into space and maybe shift it over to the right. But since it's an infinite plane, you don't really see the shift to the right. But every point on u is then shifted by the same amount, the vector v. If the vector v had only a y-coordinate, let's say v is equal to 0, 2, that means this plane, the u-plane, is shifted up 2 units. So in other words, now the z-coordinate will be equal to 2. If you want to know exactly how far up this plane is shifted for an arbitrary vector v, then you would need to know the projection of this down. So you would have to calculate the perpendicular using projections, and that's a topic you learned about in vector calc and not something that we're going to go over in this video. Now that we have this definition of a vector plus a subspace U, we're going to use that and call it an affine subset of V. So an affine subset of V is a subset of V of the form vector V plus U for some vector V in V and U some subspace of V. And then we're going to use this definition of an affine subset to define what it is to be parallel to a subspace. So it needs to be an affine subset where U is offset by a vector V. We will look at our two previous examples. First, this one here, where U was the line going through 0, 0, where the value of y was twice the value of x. And then this example here, where U was the xy plane and R3 where z is equal to 0. So first, looking at our line U to illustrate the idea of affine, then 1720 plus U is one of the affine subsets of V. And 17 plus U is also parallel to U because it's shifted over by the same amount. 1020 plus U is also an affine subset of V. Any vector from V plus U is going to be an affine subset of V. Now looking at this example, our plane, our vector V plus U is an affine subset of V, and the plane V plus U is parallel to the plane U. We have this important note here. With the definition of parallel given above when we talked about affine subsets, no line in R3 is considered to be an affine subset that is parallel to the plane U. So in other words, if I have this green line here that is totally contained in this plane U plus V, we would not say that this line is parallel to U, even though the line will never intersect U. And that's kind of the definition of parallel we learned from geometry. But in this case, to be parallel means you're an affine subset. So in other words, you need to basically offset the entire subspace U. And this one single line might be, I don't know, this line in U that is offset by V, but it's not the entire plane offset by V, so that line would not be considered parallel. And now finally, we're ready to define quotient spaces. Suppose U is a subset of V, then the quotient space V over U is the set of all affine subsets of V parallel to U. In other words, V over U, or the quotient space, is equal to vector V plus U for all vectors V in U. In other words, the quotient space gathers up all the affine subsets V plus U into a space. Looking at our previous two examples again, here we have the line U that goes from 0, 0 with slope 2x in R2. We noted that 1720 plus U is an affine subset of V, and any vector plus U is an affine subset, which means our quotient space now, our R2 over U, is going to be the set of all lines in R2 with slope equal to 2. In our next example, where U is the xy plane in R3, then, our quotient space, R3 over U, is a set of all planes parallel to U. So what these quotient spaces are doing is it's grouping together subspaces that are parallel, and they're kind of calling them somehow equivalent. So in other words, in this case, it's grouping all the lines that are parallel to U, and in this case, it's grouping all the lines parallel to U. And by grouping them together, we're kind of calling them equivalent or showing their similarity. So this is an aside, and if it doesn't help you, don't worry about it, but maybe this will help you. So I think of these quotient spaces as sort of like an equivalence relation. So if you've had, I don't know, abstract algebra, real analysis, or anything where you talked about relations, you might have heard of equivalence relations. And when I first introduce equivalence relations, I usually use this example of rolling two die. So this matrix here represents all the possibilities for a roll of two die. You can get both die are equal to 1, or the first die is 1, the second die is 2, the first die is 1, the second die is 3, or it could be that the first die is 2, so the dies are different colors. So the first die is 2, the second die is 1. These are all the possibilities. And the thing is, often you want to consider the sum of the die. So here, the sum of the die is 2. On this diagonal, the sum of the dies are 3. Here, the sum of the dies are 4. The sum of the dies are 5. The sum of the dies are 6. And you can go on and do the other rows. But the idea is all of these rolls of die, the 5, 1, 4, 2, 3, 3, 2, 4, and 1, 5, they're all equivalent in that they sum to 6. Obviously, they're not the same, right? 3, 3 is not the same as rolling 2, 4. But for our purposes, we're going to call them equivalent because we're really only concerned about the sum, which is 6. In the same way, the quotient spaces sort of says the important part of this, if we kind of like divide out the U, the particulars of U, but just look at the big pattern of U. In this case, the particulars of U is that you're starting at 0, 0. And then you're looking at the big pattern, which is the slope. And then from there, we're looking to see all the other lines that are equivalent. And in this case, equivalence means that they're parallel. And of course, parallel is this special definition, which maybe I've just walked ourselves in a circle. But that's kind of my idea. I think of this quotient space as calling all these parallel lines, in this case parallel planes, is somehow they have something to make them equivalent, not equal, not the same, but somehow equivalent. Next, we have this theorem that says two affine subsets parallel to U are either equal or disjoint. And the theorem says suppose U is a subspace of V, and the vector V and vector W are elements of V, then the following are equivalent. 1, V minus W is in U. 2, vector V plus U equals vector W plus U. And C, vector V plus U intersected with vector W plus U is not equal to the empty set. To prove that these statements are equivalent, I'm going to prove that A implies B, B implies C, and then C implies A. So this is the kind of proofs: A to B, B to C, and then C to A. And then from there, you automatically get A to C because that's A to B to C. Or you can get B to A because that's B to C to A, and you can keep doing the circle around. We are going to start with A implies B. That is, if V minus W is in U, then B, V plus U is equal to W plus U. So we're going to start again. Given V minus W is in U, to show the equality, we're going to use this strategy that we have from set theory. So if we're trying to prove two sets A and B are equal, A equals B, then what we do is first prove that A is a subset of B, and then second, B is a subset of A. Once we've proven these two things for them both to be true, it must be that A is equal to B. So we're going to start with now that V plus U is a subset of W plus U. So we're given, if we have an element U in the set U, then V plus U is equal to V plus U, and then we can add a W minus W. because that's just 0. So we add them together. We're going to regroup them. So we have W. We're going to group the minus W with V, and then we have our U. We're just going to switch the order of the W and V, which from our assumption is in U. So this is in U. We started off with this vector U is in the subspace U. So that means W plus these two things are from U. So this must be a subset. This part here must be a subset of W plus U. And I just kind of then wrote then this V plus U is a subset of W plus U. Okay, similarly, we can show that the W plus U is a subset of V plus U. So we're going to start with W plus U. We add the V and the minus V. We kind of regroup so that we have our V and then we have our W minus V and then our U. We're going to put a minus over here so that we get V minus W, which again, according to our starting assumption is in U. Of course, our U over here was in U, which means our minus V minus U plus this U still is in U. Thus, our V minus this here is an element of V plus U. So V plus U now, oh, I should go this way. Our W plus U is in V plus U, so W plus U is a subset of V plus U. Now we have our two, we have this form now, A is a subset of B, B is a subset of A. So V plus U is a subset of U plus W plus W is a subset of V plus W. That must mean that these two are equal. V plus U is equal to W plus U. For B implies C, so part B is V plus U is equal to W plus U, and we want that to imply C, which is V plus U intersected with W plus U is not equal to the null set. Well, if they're equal, they're going to have a non-empty intersection. So that one's pretty straightforward. And now to go from C to A. So C is V plus U intersected with W plus U is not empty. Then we want to show that A is true, V minus W is in U. So if V plus U intersected with W plus U is not empty, then there exists a U1 and U2 such that V plus U1 is equal to W plus U2. So what we're saying is this V plus U1, that's from this set, this V plus set U. This W plus U2, that's from this set, W plus U2. And there's something, if the intersection is not equal, there is a U1, U2 such that these two are in common, that this is where the intersection is. Now we can move this W over and get V minus W, move this U1 over, get U2 minus U1. This means that this is an element of U. So V minus W is an element of U, which is what we wanted to prove, part A. C implies A. And we're done with that proof. We can define the addition and scalar multiplication on the quotient spaces. So if we have V plus U and we add that to W plus U, then we can add our V plus W and then add that to U, and that'll be our addition. For scalar multiplication, a scalar A times V plus U is equal to the scalar A times V plus U. And with this scalar addition and scalar multiplication, we can say that the quotient space is a vector space. So suppose U is a subspace of V, then the quotient space V over U, with the operations addition and scalar multiplication as defined above, is a vector space. Next, we can talk about the quotient map. Next, we're going to find the quotient map. So suppose U is a subspace of U. We're going to define the quotient map as a linear map from V to the quotient space V over U defined by, and you know what? I'm just going to see if we can kind of guess what this definition should be because it's almost obvious. So we want to define this quotient map. We're going to call it pi. It goes from the vector space V to the quotient space V over U. How do we define V over U? It's equal to the vector V plus U. So let's think about it. If the quotient space pi takes a vector V and we want it to equal to some quotient space, V over U, the obvious quotient space then is going to be V plus u, right? It's exactly this if we want a quotient space. And that's what I'm going to write over here as my definition. Our quotient map pi goes from V to the quotient space V over U, which is simply pi takes a vector V and it maps it to V plus U. And let's look at this, our example again with our line of slope 2. So the quotient space R2 over U is equal to all the lines with slope 2. So the quotient map goes from R2, it takes a vector, and it gives us one of the lines with slope 2. So if we give it a vector V, we want V plus U. So in other words, if we gave it the vector 1720, the line with slope 2 that we want for 1720 is the one that adds 1720 to every point on U. That was our original example. Here, the original line, U, would be pi of 0, 0. That would just give us U. So the quotient map is sort of the fancy way of expressing that we're going to take a point and get a quotient space. And then we also have this theorem that the dimension of a quotient space, so suppose V is a finite dimensional vector space and U is a subspace of V, then the dimension of the quotient space V over U is equal to dimension of V minus dimension of U. Our last topic is that of the induced map, which we denote with this tilde t. Suppose T is a linear map from V to W. Define the induced map tilde t, quotient space V over null of t to W by tilde t of V plus null of t is equal to TV. And this is where an example I think will be helpful. Let's say we have this map T that goes from R2 to R1. So T of Z1, Z2 is equal to Z1 plus 2Z2. We want to find a basis for the null space to start because we're talking about the null of T. So T of Z1, Z2 is equal to Z1 plus 2Z2. To find the null space, we set this equal to 0. And we see those are the points where Z1 is equal to minus 2Z2. In other words, our bases can be expressed as minus 2, 1. This is a basis for the null of T. It's dimension 1. And again, what you see is that the x is equal to twice y. So in other words, the slope is equal to minus 1/2. So the null of T looks like the line, does it even contain 0, 0? Yeah, it contains the point 0, 0, and it has a slope of negative 1/2. So it goes over 1 and down 2. Did I do this wrong? I drew my picture wrong, so here it is corrected. So the nullity is the line through 0, 0 with slope negative 1/2. Again, our vector space is R2, our original vector space, and our W we map to R. Now then our quotient space of V over null of T, that's going to be all the lines that are parallel, that have slope minus 1/2. So for example, this is 1, 1 plus null of T. So this is in the quotient space. Now our induced map goes from V null of T. In other words, it goes from one of these lines over to R. And it's defined by TV plus null of T is equal to TV. So our induced map now, I'm going to take my line, my 1, 1 plus null of T, I need to map it to the real numbers. And the way we do this is it's going to be equal to, by definition, T of V. So that's T of 1, 1. So plugging in 1, 1 into our original transformation gives us 3. And we have this theorem that I'm going to state without proof. So suppose T is a linear map from V to W, then 1, our induced map T tilde is a linear map from V null of T to W. 2, this induced map T tilde is injective. 3, the range of the induced map T tilde equals the range T. And then the quotient space V over null of T is isomorphic to the range of the induced map T tilde. To review what we've covered in this video, we talked about quotients of vector spaces. The first thing we did is we reviewed products of vector spaces. So suppose V1, V2, Vm are vector spaces over subfield F, then the product v1 cross v2 cross up to vm is defined by the m tuple of vectors v1, v2, vm, where the first vector v1 is an element of the first vector space, the second vector v2 is an element of the second space, and essentially the ith vector vm is an element of the ith vector space. We started our exploration of quotients of vector space with this definition of a vector v plus a subspace u, both from the vector space v, and that's defined to be the vectors v plus the vector u for all vectors u and v. And what we saw is essentially that v will offset our subspace u by our vector v. The set that we get when we add this vector v to u is called the affine subset of v. And this affine subset is how we define an object being parallel to u. Next, we group all of our affine subsets for a subspace u, and we call it a quotient space. So suppose u is a subspace of v, then the quotient space, which we note v over u, is a set of all affine subsets of v parallel to u. In other words, the quotient space v over u is equal to v plus u for all v in the vector space v. We have this theorem that says two affine subsets parallel to u are either equal or disjoint. And then over here, we define addition and scalar multiplication on our quotient space. So if we have our set vector v plus u plus our other set vector w plus u, when we want to combine them, we can combine our vectors v and w and then add it to our subspace. Similarly, we have scalar multiplication. A scalar a times our set vector v plus u is equal to a times our vector v plus our subspace u. And then once we have defined addition and scalar multiplication, we come up with this theorem that says the quotient space is a vector space. Our next topic was of the quotient map. So suppose u is a subspace of v, then the quotient map is a linear map from v to the quotient space of v over u. So v takes a vector and it maps it to v over u. So v takes a vector v. To get to the quotient space, we can just add u, our subspace u, to the vector v. Next, we have this theorem for the dimension of a quotient space. Suppose v is a finite dimensional vector space and u is a subspace of v, then the dimension of the quotient space v over u is equal dimension of v minus dimension of u. And our final topic was of the induced map T tilde. Suppose T is a linear map from v to w. We defined the induced map T tilde as a map going from the quotient space of v over null of t to w, and we defined it as T tilde v of null of t is equal to t of v. And then we have this additional theorem here. And that's it for this video. Thank you for watching.